like I sound like one of those gurus on YouTube commercials. Let me teach you the secrets that they don't teach you in school, you know. But anyway, I digress. Welcome back to section K.1. I want to apologize right off the bat. I lied to you in the last video. I said that this one would just be on the comparison test and the limit comparison tests, but oh heck, let's just do P series and the integral test as well, huh? The book saves the P series for like the last page of the section. I think that's ridiculous. It's a simple one, and it'll help us with some examples as we go through the other tests. So up top, the series 1 over n to the power of p converges if p is greater than 1, diverges if p is less than or equal to 1. Compare that to down below. This was the p integral. We saw this in section I. Notice the similarities between the two of them. All right. So that's helpful. We have like kind of like fewer things to memorize now, almost. Now they're related, but they're different, right? So the series is kind of considering like the sum of just the heights of, say, these green bars. So like if this was, you know, like 1, 2, 3, 4, and so on, and our series is starting at 1. So the series is just taking this y value plus this y value plus this y value and so on, whereas the integral is actually looking at the entire area under the curve, and yet their convergence or divergence is reliant upon the same value of the exponent p. And just like with integrals, we said that like this number 1 really didn't matter. The result was going to be true for the integral of really any positive number to infinity. This was going to be the exact same. And the same will hold true with our series. It does not need to be series starting at n equals 1. It could start at any constant we want. So okay, the P series is easy. Okay, I've nothing. There's no challenging questions here, right? I'm not going to ask you, hey, you know, does that converge? Yes. But we can use this now for other tests. So here's our next test, the comparison test. Again, down at the bottom, something we've seen before was the comparison test for integrals. Notice the connection here, the similarities between that and the integral test for series. So it's the same thing. If we know that we have a convergent series, and we know that that happens to be larger than or equal to some other series, and when we say that a series is greater than or equal to another series, we mean that if I look at the third term of one series, it needs to be greater than or equal to the third term of the other series, and that needs to be true for every term. Anyway, if the larger series is known to be convergent, then the smaller series must also be convergent. If the smaller series is known to be divergent, so in this case we'll have b sub n be the smaller one, then the larger one has to also be divergent. So really the same idea as what we saw with the comparison test for integrals. First thing I'm going to check, nth term test. As n approaches infinity, yeah, this sequence does approach 0, so can't use that one. Is it geometric? No, it is not geometric. While I do have 3 to the power of n, that would be geometric. The square root of n is going to screw that up, so can't use that. Is it telescoping? I guess I could try to rewrite this maybe into something over the square root of n plus something else over 3 to the n, although if you think about that, you're going to end up with an a times 3 to the n term, and you're not going to be able to eliminate the a, as 3 to the power of n will not be equal to 0. So that technique's out. So the only thing that we have left at this moment is the comparison test. What are we going to compare it to? I would recommend 1 over 3 to the n. My only other choice would be 1 over the square root of n, which is n to the 1/2. Actually, let's consider both of these. First thing we're going to do if we are comparing is we should determine whether the series we're looking at is greater than or less than the original series. In both of these cases, the series written in blue is greater than the original series. I know that by looking at their denominators. Each of their denominators is smaller than the denominator of the original, which makes each of their overall fractions larger than the original. Take a moment, think that over. That's how we're going to evaluate whether it's greater than or less than the original. Now that I know that they're both greater than the original one, we need to show that the series we're going to use is convergent, because the comparison test, if you have a larger series, it needs to be a convergent one. So this one we're going to toss out because that's a p series, but the p-value is less than 1, so that's going to diverge. But on the left, we have something that is going to converge. This is a geometric series, right? Because that's 1 over 3 to the power of n. So my answer to this problem would be, yes, the series converges by comparison. So I'm showing the grader what test I'm using, and then I'm going to state, what series I use. So by comparison with 1 over 3 to the n. And then I might make a note that says, that this series converges because it's geometric, with r less than 1. There you go. That's the work for a comparison test. And let me just say the key to the comparison test is finding a series that you know. And the series that you know is very likely to be either a p-series or a geometric series. So in this case, we were able to find both of them by looking at the original fraction and just saying, oh, hey, that denominator, it factors. So let me just look at one particular factor of this original fraction. And then sometimes you're only going to have one option that would make sense. I mean, if this had been 1 over, I don't know, like e to the power of, no, that's still exponential. If it had been n to the power of e times 3 to the n, I'm going to ignore that particular factor. And I'm just going to look at that one because that's geometric, so I know I can work with that. It's not always going to be factorable, however. Now I'll show you one technique that I would often try with this one that it's actually not going to work in this case, unfortunately. But one thing you may try to do is to ignore part of the denominator if you can't factor it. So in this case, I might compare this series to 1 over n squared to the 1/3, which is 1 over n to the 2/3. This series that I've now made is a p-series, so I can use that. The series diverges because p is less than 1. However, when I compare these two, the series that I've just created is actually larger than the original series. I know it's larger than it because the denominator itself is smaller than the original one. N squared is going to be smaller than n squared plus 3, which means that the 1 over it, it's going to end up being larger. So I've come up with a larger divergent series, so I can't use that comparison here. So we're going to have to do something a little bit more complicated. So I'm going to set up a comparison. In this case, I'm going to show that 1 over n is actually less than or equal to 1 over n squared plus 3 to the 1/3. It's not an obvious thing to think of, so perhaps in this problem it might suggest, the problem might say, use a comparison with 1 over n to show that this series converges or diverges. I mean, since I'm comparing it with 1 over n and saying that it's less than it, then obviously the series is going to diverge. So let's see how that would look. So if this inequality is true, then that means that we could rewrite this whole thing as n cubed is going to be greater than or equal to n squared plus 3. And then we can kind of shift everything over to one side. So we got n cubed minus n squared minus 3 has to be greater than or equal to 0. And how can we show that that's going to be true? It's not obvious that it's always true. Certainly for large numbers, it will be. So the way we're going to do this is we're going to think about f of x equal to x cubed minus x squared minus 3. And we're going to actually calculate f prime. F prime of x, 3x squared minus 2x. What can I say about that function? Well, I know that f prime of x is going to be greater than 0 whenever, well, let's factor this out, huh? That's going to be 3x minus 2. So f of prime of x is going to be greater than 0 whenever x is less than 0 or when x is greater than 2/3. But remember that when we're thinking about this function, we only really care about the integer values that are relevant to our series, and our series actually starts at 2. So I don't even care about that. I really only care about x greater than or equal to 2, which is covered here. So I can say for sure that my series is increasing with every successive term. Does that mean that every successive term is in fact positive? Well, put in 2 into here. You will get a positive number. You'll actually get 1. So that means that this function, starting from x is greater than or equal to 2, that this function is always going to be positive. Because, again, the very first value is a positive number, and we've shown that it is always increasing as its derivative is greater than 0 as well. So that means that this is true, which means that this is true, which means that this is true. Ta-da! We just found a divergent series that is less than the series that, or equal to, the series in question. Therefore, this series diverges. And I would write down, it diverges by the comparison test with 1 over n, with this work over here to justify it. Now the good news is that if you didn't like this technique, there is, I think, a better technique to use on this problem. The bad news is that we're still going to need to do this whole like derivative stuff sometimes, so it is important that you have seen and experienced this. But let's see what that other technique might be. It is the limit comparison test. So we don't have anything from section I to compare this to. This is brand new. All right. So like the comparison test, we're going to have a series that is given to us in the problem, and then there's going to be a second series that we're going to kind of invent. And we're going to take a limit as n approaches infinity, hence the name limit comparison test. And we're going to take the limit of the quotient of the two sequences. Okay, the book has a sub n over b sub n. The order doesn't matter. You can do this with b sub n over a sub n. And it also doesn't matter which one of these series is, the original one from the problem and which is the one that we've made up. So don't stress about that. Okay, one of three things is going to happen. The limit might be 0. And the limit is going to be 0 if this particular series is bigger than the one in the numerator. So if that's true, and b sub n converges, then a sub n is also going to converge. And think about the comparison test for a second. We know that if we have a larger series that converges, then a smaller one also has to converge. And I just said that b sub n is going to have to be larger for the limit to be 0, right? Just thinking about that's basic limit stuff that we've known for a long time. So if b is bigger and we've worked out that b converges, then yeah, by comparison, then a has to also converge. We could get infinity out for the limit. That's going to happen if a sub n is much bigger. So in this case, b sub n is smaller. And if b sub n diverges, well, it's a smaller sequence. So therefore, the series of a sub n has to also diverge. Okay, the third option is that we might get some constant number out. They're saying here that the constant has to be greater than 0. That's definitely true since we're presupposing that the series have positive terms. In fact, everything in this video is specifically about series with positive terms. When we start dealing with series that have positive or negative terms, or both, um, or all negative, then we have some other techniques. But for right now, everything's positive for all these examples. Anyhow, when we, if we just get a constant value out, then the series either both, this is key, both converge or both diverge. And situation 1 is going to be where the magic happens. It seems like there's a lot going on in this thing, right? But the secret that is not really communicated in the textbook is that we're always going to, when we do this, we're going to make situation 1 happen. In fact, when I do it, I'm going to always look to make sure that that C value is equal to 1. That just ends up being the easiest thing to do most of the time. All right, so like deep breath, there's a lot on this screen, but if we really just focus on making C1 and then knowing that they're going to either both converge or both diverge, and finally knowing that the series that we invent is going to be either geometric or a p-series, so we'll know whether it converges or diverges, then we'll easily be able to figure out whether the other one does as well. So let's look at that previous example now using the limit comparison test. So remember before I wanted to use a comparison and it ended up not working? So if I was doing this problem, I would have first tried that comparison with 1 over n squared to the 1/3, and then when I saw that it didn't work, probably what I would have tried immediately afterwards is a limit comparison with that same exact series. So this will often work for us. So that's another little tip that the book doesn't really lead you towards. So if a comparison doesn't work with a series, try a limit comparison with that same one. So here I've got the original series, or the original sequence expression in my numerator, the made-up one in the denominator. Let's just rewrite that. That's since we've got some reciprocals here. This is going to be n to the 2/3 over n squared plus 3 to the 1/3. Now what is the limit as n approaches infinity here? It's going to be 1. Right? Because we're going to have n to the 2/3 over n to the 2/3. Since I have a positive value out, that means they either both diverge or they both converge. And I know that this one diverges because it's a p-series, which means this one has to diverge as well. For my final answer on an exam, I show this work up here, and then I write a reasoning statement communicating what I've done and why. I'm saying the series diverges by the limit comparison, so I'm identifying what test I've used. You can say by limit comparison with, or you can say by the limit comparison test, however you want to phrase that. And then I'm stating what the other series was that I used in the limit comparison. So I'm sure you all agree this was a much nicer technique than the first one that I showed you. But we needed to have the limit comparison test in order to do that. So now let's do one more. So this one, spoiler alert, it converges. We're told that. That's all right, and we're going to show that it converges. So as always, I start off, well, I won't have to think about the nth term test because that only tells me that something diverges. So the next thing, is it geometric? Clearly not. Perhaps I could try a comparison. I might try to compare this with n squared over n to the 4th, which is really 1 over n squared. 1 over n squared converges, but 1 over n squared is going to end up being less than this series because the denominator here is bigger than the denominator here, which makes 1 over n squared, or n squared over n to the fourth, less than the original series. So I can't use it for comparison. Oh, but if I can't use it for comparison, then I should try it as a limit comparison. So you see how easy this is when you know, like, what secrets to use. And again, like, I've never read this in any textbook. So I rewrite that as multiplication. I cancel some stuff. Clearly the limit here is going to be equal to 1, which again means they either both converge or they both diverge, but I know that this one converges, therefore this one also converges. Limit comparison test, there it is. Try a comparison, it doesn't work, try the limit comparison test. You should get a limit of 1, and it should work out. Is this going to work out every single time? No. But the times when it does work out, this is often how to stumble into it. One more limit comparison really fast. I'm going to try a comparison, in this case with the square root of n squared. Now n squared is less than n squared plus 4. So my denominator is smaller, which means that the whole fraction is greater than this one over here. Unfortunately, that can be simplified to 1 over n. And that p series is going to diverge. So I have a larger series that is divergent. So the comparison test doesn't work. So instead, we try the limit comparison test. This is going to be the limit as n approaches infinity of 1 over square root of n squared plus 4 multiplied by square root of n squared over 1. My limit here is going to be, as always, 1. So they either both converge or they both diverge. That one diverges as it's a p-series. Therefore, this one diverges by limit comparison. Ta-da! Final test for this video is the integral test. So the integral test, we're going to consider our series, or excuse me, we're going to consider our sequence as a function, like we talked about last video, and we're going to consider the integral of that function. Turns out, if the integral is convergent, then the series is also convergent. If the integral is divergent, then the series is divergent. So we saw how to evaluate improper integrals of this form back in section I. So we're just going to do that again here. The integral test is certainly not one that I try out first. I'm going to always try to use a comparison or a limit comparison before I try an integral test because this one tends to just take more time. So here's our first series. Does it converge? As always, I check my nth term test. Yeah, limit as n approaches infinity. This sequence will approach 0, passes the nth term test. Next, I check is it geometric? No, it's not geometric, so I can't use anything there. If it were me doing this one, I would use a comparison. I'd compare it to n over n squared squared, which can simplify to 1 over n cubed. 1 over n cubed is a p-series. It converges. And n squared is less than n squared plus 1, which makes this entire series greater than this entire series. So I have a larger convergent series, so by comparison, the series in question must also converge. So really a comparison would be the easiest thing to do here. But just in case the problem told me that I need to use the integral test, let's do the integral test. Rewind for just a moment. I'm going to need to show that my function is continuous, positive, and decreasing. Okay, compare that to last video. We thought about sequences being monotonically increasing or decreasing and also bounded. Well, this is going to be a function which is monotonically decreasing, but is also bounded below as it must be positive. So let's show that here. So we're going to be interested in f of x equals x over x squared plus 1 squared. First thing I'd like to show, well, first of all, it's definitely going to be continuous for well, this is going to be continuous for all real numbers, but really I'm only interested in x greater than or equal to 1, as that's where my series starts. But if we just look at the denominator here, that's definitely continuous for everything. This is also going to be positive for all x. I don't even need to say equal to 0, because we've already stated that x has to be positive because it's greater than or equal to 1. And then our denominator is something squared, so that's going to be positive. So I have a positive divided by a positive. So it's definitely going to be greater than 0. We need to state these things if we're going to use the integral test, by the way. I need to state that f of x is continuous on the important domain. I need to state that it's greater than 0. I might say something about like positive divided by a positive just to note it, but most of the mark schemes that I can think of, they just have you making this statement. So like you're kind of just, even if you have no clue how to test it, just I don't know, just say that it's continuous, say that it's 0, and maybe you'll squeak by and get lucky. Anyway, now we need to show that it's decreasing. Well, we talked about this earlier. We're going to show that it's decreasing by considering its derivative. So for this, we need the quotient rule. It's going to end up being 1 minus 3x squared divided by x squared plus 1 cubed. You can take a moment to work that out on your own if you like. Now this is going to be always negative because, again, as x is bigger than or equal to 1, the denominator is going to always be positive, but the numerator is going to always be negative. So therefore, the derivative itself is negative. So finally, I have a continuous positive decreasing function here for sure. Now we can use the integral test. So that was going to be the integral from 1 to infinity of the function that we're dealing with, which is really going to be the limit as some constant, or excuse me, some variable b goes to infinity of the integral from 1 to b. And then to evaluate that particular integral there, we're going to need to use u substitution. So we're setting u equal to x squared plus 1, which gives the du is equal to 2x. So half of du is equal to dx. Blah, blah, blah. Eventually, we're going to get a limit out of this, or excuse me, a value out of this integral. I'll let you have the fun of reviewing section I to see that. It ends up coming out to be equal to 1/4. So the integral, the indefinite integral, converges to a very specific value of 1/4. That means that the series also converges. It does not converge to 1/4. We have no idea what it converges to, but we have shown that it does converge. I hope you can see why I prefer the comparison test and the limit comparison test, or pretty much any test, I think, to the integral test. I would say that's almost definitely my least favorite one. But sometimes it's all we got, because we're not going to be able to use a comparison or a limit comparison on this one. We could try splitting up this series into factors. So I could try 1 over n. 1 over n diverges, but the series of 1 over n is going to end up being bigger than that one because the denominator is smaller. But then if I try a limit comparison, I'm going to have 1k times just n. The n's are going to cancel, and now I'm left with a limit of 0 as n approaches infinity. And if we were to rewind really quickly to the limit comparison test, if the limit is equal to 0, if our secret, if our made-up function converges, then the original one converges. But unfortunately, that's not the case here. 1 over n does not converge. So that doesn't show us anything about the original. So both a comparison and a limit comparison for 1 over n don't work. I could try looking at 1 over ln of n squared. I don't know if that converges. I mean, it's clearly bigger than the original one, but I don't know if it converges because it's not a p-series and it's not geometric. And I'm going to end up with the exact same problem if I try a limit comparison with that one. I'm going to end up with 0 as my limit. So since none of the techniques we've seen so far work, the only thing that we could perhaps try here is an integral test. So I will show you the work for that. Here it is in almost all of its glory. We start off with the original integral evaluated here, or written, excuse me, as a limit as b approaches infinity. We're going to have to use substitution again. Thankfully, this substitution is very nice and neat. We end up with this integral here. 1 over u squared is, of course, u to the negative 2. So we'll just use the power rule to integrate this. I've changed the limits of integration. So technical point, when you use substitution, you should always change the limits. And those are formed with this. So my new limit, I just put the original limit into x. So this was 2. So the lower limit will be ln of 2. The upper one was b. So now I have ln of b. As a technical note, I'm not sure if that limit should be changed to b or to ln of b. It's not something I could find an example of. I mean, it doesn't really matter as b approaches infinity. Ln of b also approaches infinity. I'm not sure though. But anyway, so we evaluate that integrand. We get negative 1 over u. When we substitute in ln of b into that, we're going to get 0, right? Because we're going to have 1 over a super, super big number. And then it'll be minus a negative, so plus 1 over ln of 2. And that is the exact value for that integral. And that's a constant. It's not infinity. So that means that the integral converged. So by the integral test, the series also converges. So there's a whole lot of tests for you now. Okay, recapping, we've got the nth term test for divergence, geometric series, comparison test, limit comparison test, p-series, which is its own test but is usually used in conjunction with something else, and we've got the integral test. A lot of different techniques. We've seen examples where some worked and some didn't. Some might be faster than others. But we need to know how to use them all because a problem might tell us to use a particular test. Okay, so that's the end of section K.1. We've got 6 different techniques at this point. Again, they are geometric series. We know that from the core. The nth term test for divergence, easy to check as a first step. The comparison test and the limit comparison test kind of go together. P-series, which is its own test, but usually is used in conjunction with other tests. And finally, the integral test, which kind of sucks, but is doable. And again, certain problems are going to be, it might be possible that multiple tests will work. Some might be faster than others, but we need to know them all because the problem might require us to use a particular method. If you're practicing at home and you just have no idea what to do, there are websites that can help you. I used to really strongly recommend Symbolab because they have a series calculator which used to show you all the steps, which was amazing. At some point in the last year, they've put that behind a paywall, so now you need an upgraded account. It will, however, still tell you what tests to use. It just won't show you the work for it. So check out this website up here. It's symbollab.com/solver/series calculator. You can just type in your series right here, and it will give you the answer down below. It'll say converges or diverges, and it'll tell you what test, but you'll still have to figure out what the work might have been going into that. If you'd like to pool your resources, and buy a class account. That would be awesome. I'm happy to organize this. If you want to pool your resources with me, I'll donate as well. Um, Let me know. Anyway, yeah, that's it for this video. We'll continue on with K.2 next time.